When we add resistive circuits to a single storage element, the resulting circuit is called a first order circuit. The storage elements that we've talked about so far are capacitors and inductors. So when you add a resistive circuit like a resistor to a single storage element, either you have a resistor and a capacitor or a resistor and an inductor, what you have as a result of that is a first order circuit, because the circuit is characterized by a first order differential equation. We will see that as we go, as we proceed. So we will be able to study along the line circuits without independent sources, and those are going to be referred to as natural response due to initial energy stored in the circuit. We're going to look at circuits with DC sources. Two additive responses will apply here. The first one will be the natural response, and then the second will be the first response, which will be based on, which will be due to the independent sources. And then we will also look at circuits with non-DC sources, and this primarily focuses on responses to step and pulse sources. So all of these we're going to discuss as we move on. So now let's talk about natural response of a simple RC circuit without sources. This time around, we're not talking about any voltage source or any current source and so on and so forth. We just want to talk about a natural response of a simple RC circuit. When you hear the term RC circuit, we're talking about a resistor and a capacitor circuit. Okay, so this is like a resistor and capacitor put together in a circuit. We'll make a very important assumption as we go on, and that assumption is the fact that the capacitor is already charged. So irrespective of the means that we have used to charge the capacitor, that is not important to us. What is important to us is that we assume that the capacitor is already charged to a voltage V0 at the initial time t equals 0. So the initial time is always t equals 0, and then we assume that we already have a capacitor already charged to a voltage V0. All right. So this also should not be a problem for you guys, because these are things we have mentioned before. So normally we usually have our voltage as V of t, right? So usually V of t is like this, or we sometimes write it as V of t. So at t equal to 0, what we are going to have is just going to be V0, or we're just going to have at t equal to 0, we're going to have V of 0. So that's what it means by the capacitor is already charged to voltage V0 at the initial time or at t equal to 0. Okay, so this is what we are referring to. If you look at this circuit, we need to determine V of t for t greater than 0. So for example, we already said that at t equal to 0, we have our V0. So we know that. Now, when t is greater than 0, what is going to be our V of t? What you want to carry out, what you want to try to do is to identify a node just at this point, because you know we have a capacitor here, we have a resistor here. So you want to create a node here where you connect the two of them. So at this particular node, this is plus here, and this is our negative here. So you have our current flowing this way. This is plus here, this is negative here. We have the current for the capacitor flowing this way. The current for passing through this resistor or flowing through this resistor is flowing from positive to negative this way, and the one flowing through the capacitor is flowing from positive to negative this way. So you can see IC and then you can see IR of T. So if you implement KCL, at this node, you know we already said that right from the beginning that current that enters a node, we represent it with a negative polarity, and then the current that leaves a node, we represent it with a positive polarity. All right, and then the sum of all currents around the particular node must be equal to 0. So what you will find out here is that IC is leaving the node, IR is also leaving the node. So that simply means both of them will carry a polarity of plus. They will carry plus signs. Both of them will carry plus sign. All right, so what you find out is that IC plus IR will be equal to 0. And then we know our IC to be C divided T from our previous studies. And we know our IR, applying Ohm's law, to be V over R, also from our previous studies. You add both of them together, you equate them to 0. So what you have here right now is a first order differential equation if you rearrange this. If you rearrange this, you can divide all the sides by C. If you do that, if you divide this by C, divide this by C, and then you divide this by C. 0 over C will still give us 0. You have our V over CR here, and then you have C here, we cancel the C. So you have just dV dt. So this is a first order differential equation. In case you're still wondering what this means, I will show you how in a couple of minutes. All right. So what you can do here is that you can now rearrange and bring all the V's to one side, and then you have all the other parameters on the other side. If you do that, what you have is you divide every other thing again by V. If you divide all the sides there by V, you have V here, and then you have V here, and then you have V here, and then you multiply all the sides by the T. So you have the T here, and then you have the T here, all right, and then you still have the T here. So 0 multiplied by the T, 0 divided by V, everything will still be 0, so you still keep 0 here. Then here the T will cancel the T, so what you're going to have left is just going to be the V over V. And then here what you would have would be this V will cancel this V, and then you have the T over CR. So that is what you do have here. If you move the T over CR to the other side here, it becomes minus the T over CR. So eventually you come up with the V over V equal to minus the T over RC. So this is very important for you guys. Let's take it a step further here. What you want to do is to integrate both sides. If you integrate both sides, you have the V over V equal to minus 1 over RC integral of the T. 1 over RC is going to be a constant. RC will be constant. Okay, so you have they are constant functions. So you have minus 1 over RC. You bring them out of the integral value, and then you have your dV over dV. This looks more like you're integrating 1 over V dV. So 1 over V will give us ln V. Okay, if you can brush up your integral, your integration skills. So you have ln V here equal to minus T over RC. If you integrate the T, it's like integrating 1 the T, it will just be T, all right? So that gives you just T here over RC. And whenever we integrate, we always add a constant value here, all right? So you have ln V equal to minus T over RC plus that constant value. Now, if you want to find V, you just take the exponential of both sides. If you take the exponential of both sides, you would have exponential of ln V equal to exponential of minus T over RC plus K, all right? So exponential of ln V will be equal to V. Okay, when you take the exponential of the ln function, what you have left is just going to be that function. So here exponential of ln V will be equal to V, and then you have exponential. When you take an exponential of addition, when you add two values together and you take the exponential, what you are going to have is going to be K exponential minus T over RC. For example, this is mathematics though, but I think because we will be doing a lot of these as we go on, probably it would be nice if I just remind you of this. Okay, so what probably you would have is exponential of minus T over RC. Okay, minus T over RC plus K. All right, this is what you're going to have. All right, so if you do have these, this can be written as exponential minus T over RC dot exponential of K. All right, so you can write it like this. Exponential of K can also give us our K, will also be the same thing as K. Okay, so eventually you have K exponential, because it's just going to be a constant. So you have K exponential minus T over RC at the end of the day. So that is why we have these here. So we got that. And then let's go ahead. Then the question you want to ask yourself now is V equal to K exponential minus T over RC. If you have that, What is K? How can we find K? How can we interpret this K? We do know from the beginning that V of 0, we know that V at t equal to 0 would be equal to V naught, isn't it? And this is one of the first few things I mentioned to you when we started. This means that our t equal to 0. That is what that means from the statement and assumption we made at the beginning here. All right. So coming back to this particular expression, we can say that V of t equal to Ke minus t over Rc. When t is equal to 0, that means wherever we see t, we just put 0 there, right? So we have V of 0 using this particular function, V of 0 using this function. V of 0 will then be equal to K exponential minus 0 over Rc. Okay, everything at the top here will therefore become 0 when 0, substitute 0 as t. So you have exponential 0. Exponential 0 will give us 1 because anything raised to power 0 is 1. So you are left with V of 0 equal to K. So what you'll be left with here is that V of 0 will be equal to K. So you can say that our K is equal to V naught. What you can do now is to rewrite this particular equation. You can then say, instead of putting K here, you put V naught there. So you say your V of t, all right, your V of t with this is a function of time. Your V of t now will be equal to V naught exponential minus t over Rc. This equation is important. You will use it almost, as often as possible as we move on. All right, let's take it a step further. So we have agreed that our V of t is equal to V naught exponential minus t over Rc. Okay, you can plot a graph for this circuit. We know this circuit already. Now you can, and then you can represent this with I of t. And then you can plot the graph of V of t against time. All you need to do is you say, okay, when your t is equal to 0, what is going to be your V? You will get a value. When your V is equal to 1, what would be your V? You will get a value. So you can keep doing that and then keep, getting different random values of t and find your V. When you have the values of V for random values of t, then you can plot a graph, and this is what the graph is going to look like, starting with V naught here. Because when t is equal to 0, your V of t will be equal to V naught. So starting from V naught right down up to when you get to V equal to 0, that is when you're going to stop. All right. So you have this kind of a function, this kind of a graph, and this kind of a function. Okay, so the natural response is also referred to as a transient response. The response of this circuit after a long time. If you remember the conversations we had in the previous classes, the response of a circuit after a long time is usually called steady state response. All right, and we've talked about that, and we've done a lot of calculations with regards to that. Okay, so you can refer to this as a transient response or natural response of a simple RC circuit. Let's talk about conservation of energy. The energy at initial time t equal to 0 stored in the capacitor will be given as this. Don't forget, we also talked about this energy in our previous class. We said for a capacitor, energy will be equal to half CV squared. So at time t equal to 0, we're going to have energy at 0, t equal to 0, then you have your V naught here. Okay, so this is what we are going to have. All right. Now, with these, at any time t, WC of t will be equal to half CV of t. We know that. And this will be equal to half C V naught. We know our V of t is equal to V naught exponential minus t over R over C. So instead of writing V naught here for this one, when our t is equal to 0, what you would have is to have, instead of writing just V of t here, instead of writing just V of t here, you will put V of t exponential minus t over RC squared here, because V of t is equal to V, as we have discussed right up here. So if you expand that, we have half C V naught squared exponential minus 2t over RC if you expand this. So your energy will be equal to, energy as a function of time will be equal to WC 0 exponential minus 2t over RC. Please don't forget that we already said that our WC of 0 is half CV naught squared. Don't forget that. WC of 0 equal to half CV naught squared. We said this, we proved this at the beginning. And if you look at what we have here, we have half CV naught squared here. So this half CV naught squared here we'll replace it with WC of 0. Okay, so instead of writing half CV naught squared here, we'll replace it with WC of 0. So that is why we have WC of 0 here, exponential minus 2t over RC. So you will find out that we have been able to express our energy at any time as a function of the energy at the initial time, the initial energy exponential minus 2t over RC. All right. Now, as t tends to infinity, what happens? The stored energy in the capacitor decays to 0 as t tends to infinity. As t increases, okay, so that is what you will see here. As t tends to infinity, as t increases, the stored energy will decay to 0. All right. Through conservation of energy, the lost energy has to go somewhere in the system. Well, where would it go? All right. And how would we represent that? Where would it go and how would we represent that? Let's see. Let's check it out now. You will see that we have WR for energy in the resistor. You would also remember in the previous studies we had that energy, stored in a resistor or energy dissipated in a resistor is usually given as integral of P dt, P tau dt, all right? Okay, so, and then we usually represent this with our time, okay? So P times dt, all right? I'm going to tell you the difference between these and the specific time very soon, but let's just take this P times dt, and then this is P of R, which is the power dissipated in the resistance, okay, in the resistor. Don't forget that our power is also equal to V squared over R. One of the expressions for power is V squared over R. So in this case, we have V squared over R here, and then we still have our expression just the way it is here, T to T, V squared over R. And then if you plan to check this out and check it out properly, you will find out that these voltage across the capacitor and voltage across the resistor, both voltages are in parallel, right? So that simply means they will be the same. So your VC will be equal to VR, all right? And they will be the same. So you can represent those as the same, okay? So if VC equal to VR, and then for our VC, we obtained a particular value, okay? So you can say that our VR here will be equal to exponential minus t over RC, because this V of t here will stand for both of them. You can put it as you can say it's equal to V of t here if you want. So when you're dealing with C, you have VC. When you're dealing with R, you have VR. VR therefore will be equal to V naught exponential minus t over RC squared over R here. Okay, so if we go ahead to expand this, what you will find is we have V naught squared over R. You can bring that out, and then you're left with exponential minus 2t, because if you squared t over RC squared would just be minus 2t over RC dt. So this is what you come up with at the end of the day. All right. Now, if you have these, how do you integrate these? All right. First of all, we have V naught squared over R outside the integral value. So we are just trying to integrate exponential. You know how to integrate exponential. First of all, you differentiate what we have at the numerator here, at the exponent. If you do that, you're going to obtain minus 2 over RC. So whatever you obtain there, you bring it as a denominator. So you have minus 2 over RC as the numerator, and then everything you have here automatically becomes exponential minus 2t over RC when you integrate it. It's just going to be the same thing when you integrate it. The only thing is that you first differentiate these, and then you make it the denominator, and then you bring everything out together. All right, so you have 0 to t. This is just basic integration, so it's not a big deal for me. Everything happening from here right up to this particular level is just mathematics and integration. All right, so you should just brush up those skills, your mathematics and integration skills up perfectly well, and then this will not be a big deal for you at all. Okay, so we are where we are right now, and then what you will find is that we have V naught squared over R multiplied by exponential minus 2t over RC, all divided by minus 2 over RC from 0 to t, because those are the limits we do have. So if you're going to substitute all of these 0 and t into this expression, what you would have is that WR of t would be equal to minus 1 over 2. As you can see, this is minus 2 here. So if you bring it up, it becomes minus 1 over 2. And then you would obtain CV naught squared, because there's V naught squared here, by the way. So there's V naught squared already. And then you will see we have C here. There is another C here, RC here. So you have CV not squared exponential minus 2t over RC. All right. You will obtain this when you substitute t is equal to t. All right. Then minus when you substitute 0 into this equation. When you substitute 0 here, you will obtain minus minus because there's minus here, then minus again will convert, two minuses will make a plus here. So you have plus half CV naught squared, okay, when you substitute 0. If you carry out simplifications, if you simplify all of these, you take common terms out, you would have half CV naught squared into bracket 1 minus exponential minus 2t over RC, close the bracket, and this would be equal to, again, this value here represents WC at t equal to 0. It represents our energy at t equal to 0. Okay, so you have WC at t equal to 0. You put that here, and then you still have this value here. All right. So what you will find out here at the end of the day is that your WR of t is equal to, this is WR of t is equal to WC of 0. If you expand this would give you WC of 0 times 1, right? So it becomes WC of 0 equal to WC multiplied by this entire expression here, okay? Minus WC of exponential minus 2t over RC, okay? So this WC multiplied by exponential minus 2t over RC represents something we already found out, which is what we do have here. Where is it? WC naught, this is WC of 0, by the way, don't forget. Okay, so this would mean WC, this would eventually represent what we have here. So instead of writing this, you can just replace it with WC of t. So that is why you have WR of t equal to WC of 0 minus WC of t. Okay, so this expression is very important. We'll use it in lots of calculations. Before we even take it a step further, you can rearrange this in as many ways as you can, right? Don't forget, you can rearrange this in as many ways as you can. If you want, now we have WR as a subject. If you want, you can make WC as a subject. If you make WC as a subject, WC of t as a subject, it becomes WC of 0 minus WR of t. All right. If you want, you can make WC of 0 as a subject. It will become WC of t plus WR of t. Okay, so you can make any one of them depending on what you're looking for, the subject of your expressions, and find what is missing. All right, let's quickly look at this simple example together. You have this circuit, and then you have V of t. You have V of t here. You have R to be 1 k ohm, that's 1 times 10 raised to power 3, 1 kilo ohms, and then you have this V of t is the voltage across this capacitor. Okay, so this is a capacitor and this is a resistor, and then you have I of t load. So the question says find I of t and then find the maximum power dissipated. All right, you have been given V of 0 to be 5 volts, so the capacitor has been charged, fully charged to V of 0 equal to 5 volts. Okay, to do that, first of all, you want to find your V of t. Okay, so V of t, for example, for the capacitor VC, it will be V, for the capacitor it will be VC of t. So that becomes VC of t equal to V naught exponential minus t over RC. That is one of the expressions we developed in the previous slide. So you have V naught exponential minus t over RC. Don't forget, we know our V naught to be 5 given here. Also, we know that our R is 1 kilo ohm, so that becomes 1 times 10 raised to power 3. That's why you have 10 raised to power 3 here. And then you have our C. Our C is given as 1 microfarad, right? 1 microfarad will mean 1 times 10 raised to power minus 6. If you simplify this, you have 5 exponential minus 1000 t volt. That is your V, voltage across the capacitor. Don't forget that our VR will be equal to VC because these two elements are in parallel. So your VR will be equal to VC, just like we mentioned earlier in the previous discussion. So that simply means since we find our VC, we can say it is equal to our VR. And from our Ohm's law, we do know that our I will be equal to V over R. Or probably if you just apply KVL here, your I of t would be equal to V R of t over R. V over R, we know it already, which is what we have calculated here. You put it right on top here. We know what our R is 1000. You put that right below here. If you simplify that or solve that, you will find out that our I of t will be equal to 0.05 exponential minus 1000 t ampere. All right, because this is 5, this is 1000. 5 over 1000 will give us 0.005 exponential base, and then exponential 1000 t. So this becomes our current I of t that we are looking for. Don't forget to find your power. Power is always equal to I squared RT. We've discussed this before. I squared T, as I squared R rather. Power is equal to I squared R. Don't forget I of T squared multiplied by R if you are dealing with it as a function of time. So power will therefore be equal to the power in the resistor, by the way. So it will therefore be equal to, if you don't want to use this, you can use current if you want. You can then say, since you have your I, you can say it will be equal to 0.005 squared multiplied by 1000, all right, which is what we have. If you multiply by 1000, it simply means that this becomes exponential 2000. This is how this 1000 became 2000, because they multiplied by 1000, all right? Don't forget, this is just pure mathematics. Otherwise, if you don't want to use I squared R, you can also use V squared over R, all right, which is exactly what we used here. So it simply means you have your V squared divided by R, which is divided by 1000. Also, you would have the same answer if you do that, okay? So that's that about how to find the power, all right? Now, this is going to be the maximum power, by the way. This PR of T is going to be the power function. This is the power function. The entire, let me make it a bit clearer. This entire expression here is a power function as a function of T. A power function, okay, as a function of T, power as a function of T. So the maximum power of the peak power will be the value that we have here as the coefficient of the exponent. Okay, so the maximum power distributed will be 25 milliwatts at the time when the capacitor starts discharging at T equal to 0. Okay, so this is a pretty simple example, and I feel and I believe this is not going to be a problem at all. All right. Today we are going to be talking more on the natural response to simple RL circuit. So you have a resistor and then you have an inductor in the circuit together to make up a circuit. So the assumption we made in the case of the capacitor is that the inductor is already charged to voltage V0 at the initial time T equals 0. In this case, the case of RL circuit, we will assume that the inductor is already magnetized by whatever means it has been magnetized to a current I0 at the initial time T equals 0. With that in mind, let us go ahead and examine this simple circuit here. First of all, what we want is, we already know that time equals 0. We know that the circuit is magnetized to current I0 at an initial time. That initial time is T equals 0. So when T is equal to 0, we have I0, or we have I of 0, okay? And that is also the same thing as I0. Now, the question would be to determine the current when T is greater than 0. That is actually, what is right before us to deal with. When T is greater than 0, what would be the current, okay? Now, if you apply KVL to this simple circuit here, you see we have an inductor and then we have a resistor here. So if you apply KVL, each one of these elements will have their respective voltages. So if you apply KVL to this entire circuit, we're going to have a VR here for our resistor, and then we're going to have a VL for our inductor. So KVL would mean that we have plus VR plus VL equal to 0, okay? So if you have those, that simply means our VL, as we know, is the same thing as L di dt. We have dealt with this when we're talking about a steady state. VL equal to L di dt. And from our Ohm's law, we know that our VR, the voltage across the resistor, will be equal to IR or RI according to Ohm's law. So adding both of them together in this equation will give us 0. Okay, so if you rearrange these, just divide all the elements in this equation by L. What you have left is di dt plus R over L I equal to 0. Okay, and then if you rearrange these by moving this entire part of the equation to the other side, what you're going to have left is the I dt equal to minus R over L I. That's what you're going to have. So if you have these, this looks more like a first order differential equation already. So probably what you can do here is you can quickly rearrange by putting all i's on one side and then putting all the other elements on the other side. So all the elements, all the part of equations with I, putting them together would mean dividing everything. This particular equation here, if you divide everything by I, divide everything by I, and then you multiply everything by the t. You divide by I, and then you multiply by the t. Okay, so what you're going to have left is going to be di over I equal to minus R over L dt. Okay, so to find your I, all you need to do is just integrate both sides. If you do that, you are going to obtain something like this at the end of the day, and that takes you to lane I. If you brush up your integration skills, you will find out that we obtain lane I equal to minus R over LT plus K, where K is the constant of the integration that we do have. Okay, so if you take the exponential of both sides, you know, you are going to have exponential of lane I, and exponential of lane I will definitely just give us I at the end of the day. So you have your I equal to K exponential of minus R over LT. So we've talked about, you know, things that are close to this before. So, but then we just need to brush over these again as we move on, because now we're dealing with RL. For RC, you know, we focused more on the voltage. But for the RL circuit, you will find out that what we have is I of t instead of V equal to KE exponential minus R over L multiplied by T. And you would agree with me that for continuity purposes, to obey the continuity principle, the I of 0 naught will be equal to I of 0 minus, which would also be equal to I of 0, okay? Which will also be equal to I of 0, and all of them will then be equal to I naught, because I of 0 is going to be equal to I naught. Okay, at the end of the day, that would mean that if you have these, it means you are making your t to be equal to 0. Okay, if you have I of 0, it simply means that you are substituting 0 for t. So if you put that in this equation, this becomes I of 0, or I naught will therefore be equal to K exponential minus R over L multiplied by 0. Everything here then becomes 0. If everything here becomes 0, it simply means exponential 0 is equal to 1. 1 times K is equal to K. So your I of 0 or I naught will therefore be equal to K. If you come back to this particular equation and you want to write your I of t, your I of t then becomes, instead of putting K here, it becomes I naught, because you found your K to be equal to I naught. All right, so your I of t will be equal to I naught exponential minus R over LT. Okay, so this is not a big deal for you at all, because we worked on some stuff that are similar to this before now. So this is not going to be a big deal for you guys at all. So let's take it a step further. So there is an alternative way to solve using characteristic equations. Okay, so you have to learn how to use these characteristic equations, because of this, because we will need it as we go on. We'll need to use this many more times as we go on. Okay, it may not appear too significant right now, but you should know how to use it. We used it in the previous discussions of the RC circuit. For the RL circuit, let's try to use it now. This time around, pay more attention to it, because you would need it. Okay, so assume a trial solution. This is just like an alternative way of finding, you know, an alternative way of finding this solution is what we want to do right now, right from the top. An alternative way of finding this solution right from the top. Okay, so let's go ahead. First of all, if you want to bring this equation here, L di dt plus Ri equal to 0, you can do that. Okay, or probably if it's this one you want to bring, you can do that. The I dt plus R over Li equals 0. They all mean the same thing. Okay, so this is the equation we obtained in the previous slide. Okay. In this particular case, we are assuming that we have a trial solution. A trial solution is like an assumed solution of this equation. So we are assuming that by the time we solve this equation, we're going to get a value I, which is equal to k exponential st. So we are assuming that I is equal to kst, which is a trial solution. Okay, it's just an assumption. If we do that, it simply means that we would have, instead of putting I here, you will put k exponential st there. So you have d k exponential st dt plus r over L k exponential st equal to 0. All right. So d dt k exponential st would mean that we're just trying to differentiate this. If you do that, what you would have here is going to be ks or sk is what you're going to have left. Sk, the exponential st dt is what you're going to have left here. All right. And this it simply means that we are just differentiating exponential st. Okay, so we have dealt with the s part, and this is just going to be the same thing as just exponential st. So if you differentiate this, the final value you will obtain will just still be sk exponential st is what you're going to obtain when you differentiate this entire stuff. Okay, so that is why you find out that there is sk exponential st here. All right, and we have our r over L k exponential st. What you will find here, if you look at this critically, what you will find eventually is that these guys are, this is like an equation we want to solve. Okay, so if you pick up the like terms here, you have ke exponential st is common to both equations. If you take this out, what you have left in the bracket will be s here for this particular part of the equation. And here, if you take KEST out, K exponential ST out, what you have left is plus R over L. This part of the equation equal to 0. This is what you're going to have left here. All right. In mathematics, this looks more like two solutions. If you either say this is equal to 0 or this is equal to 0 will be the solution to this equation. And as we know, all right, right from when we started, I told us that K exponential ST can never be equal to 0. K exponential st cannot be equal to 0. Okay, so that means we cannot equate this to 0. So the only solution we are left with to deal with that will be s plus r. So we can easily say that, okay, if k exponential st cannot be equal to 0, so we say s over s plus r over L then is the only part of this equation that will be equal to 0. Okay, if you do that, what you find out is that your s will be equal to minus R over L. Okay, so if your S is minus R over L and you had initially said that your solution is K, your trial solution is K exponential ST. So you can easily see that your current that you're looking for I of t would be, instead of writing K exponential ST, we found S already to be minus R over L. This becomes K exponential minus R over L multiplied by T. All right, using the same initial conditions that we used in the previous discussion, you find out that your I of naught will also be equal to K. So you just replace this K with I naught, and then that is the initial condition when T is 0. And then you have your final I of T, which is exactly what we obtained. If you look at the present discussion we had, this is exactly what we obtained. So I have to just show you another method by which you can obtain this I of T. And then it's a useful method because it will still be used again. That is why we had to go through this now. All right, let's go ahead. A simple example that we can apply to our understanding. Just a very simple example. In this example, we have an inductor in the circuit, and then we have a resistor. You see that we have been given that our VL is 10 exponential minus 200t for t greater than 0. All right, so we are looking for the inductance, and then we are looking for the initial current I naught. So how do we find those? Okay, first of all, you know that our VL is equal to minus L di dt. So our voltage induced on the inductance here would be minus L di dt. Don't forget that at the beginning we had said that VL plus VR equal to 0. So it simply means that if our VL is minus the I the t, it simply means that VR from this equation will be equal to minus VL from this particular equation. So VR will be equal to minus VL from this equation. So if our VL is minus this, it simply means this is automatically just going to be equal to our VR. Okay, so VR is Ri. So minus L di dt will certainly be equal to Ri. Okay, and that is also going to be equal to 10 exponential minus 200 multiplied by t. Okay, so this is sorted out. Then again, our IL, from what we do know, our IL is usually equal to our IL, like we have done in previous times, is going to be equal to minus 1 over L, if you remember, integral of VL dt. And that can also be obtained from here if you choose to find I by integrating both sides. This is what you are going to obtain. So I will be equal to minus 1 over L, okay, VL dt. This is what you're going to obtain from 0 to t. Okay, so that's what we do have here. We know our VL is 10 exponential minus 200t. So you can replace this VL here with 10 exponential minus 200t. Your 1 over L is still here. You can take it out or leave it inside if you want. So if you integrate 10 exponential minus 200t, what do you have? What would you obtain if you integrate these? Okay, first of all, you can take 10 out. So if you take 10 out, you just have 10 here. Okay, and then if you to integrate exponential of minus 200t, you know what to do. This becomes minus 200. If you differentiate what we have up here, it becomes minus 200. You're going to have to bring that here, minus 200 here. If you do these, and what you're going to have left is just going to be exponential. By the way, you still have 1 over L somewhere here. Okay, so what you're going to have left is exponential minus 200t if you integrate these. Okay, this is what you're going to have as your VL eventually if you integrate, as your IL rather. So this is what you're going to have as your IL eventually if you integrate these. Okay, so you see that, by the way, this is minus 200 here, and there's one minus is already here before now. Don't forget there's a minus here before the integration started. There's a minus here, so you can keep that minus here. So this minus will certainly cancel out this minus, and 0 will cancel out, and 0 here. So what you have left is that your IL will be equal to 1 over 20. Okay, so you have 1 over 20 L exponential minus 200t. This is very important for us. Also, don't forget that our IR, we can easily find our IR, okay, the current passing through these resistor or the resistance here. So according to Ohm's law, IR will be equal to VL over R. We know our VL is 10 exponential minus 200t, as we have right up here, divided by R. Our R is 1K, 1,000 ohms. So you put your 1,000 ohms here. So if you solve this, what you have is this 10 will cancel this here, and then you have exponential minus 200t over 100. Okay, don't forget that your IL will be equal to IR. Okay, don't forget that IL will be equal to IR. We have explained this too in the previous classes, previous discussions that we had. So you can say that 1 over 20 L exponential minus 200t is equal to exponential minus 200t over 100. Okay, if you do that, what you find out is that this will cancel this, and you have just 20L will be equal to 100, and so L will be equal to 100 over 20. L will just be equal to 100 over 20, and that will give you 5. So you can say that your inductance will be equal to 5 Henry according to what we have here. Okay, inductance will be equal to 5 Henry. Okay, and then if you're looking for your I naught, it is the initial current I naught is always what we have here. Don't forget. Okay, your IL is usually equal to I naught, then all the exponential values follow. Okay, so it simply means that your I naught would be equal to 1 over 20 L. If you know your L to be 5, your I naught would therefore be 1 over 20 to be 5, and that gives us 1 over 100, which is the same thing as 10 milliamperes. All right, so this is a simple example for a basic circuit, and once you understand this, it makes it easier for you to be able to deal with complex circuit when you're faced with one, as we will see as time unfolds. So if you have any question about this, you can ask me, you can point it out so we can look at it and deal with it together. Otherwise, we can just go ahead, or you can just send the questions to me via chat or post the questions as a comment and I will try to deal with it. Okay. Let's talk about the time constant. The time constant is usually given as tau. Okay, this symbol here is called tau. It characterizes the rate of decay for natural response. So it is defined as the time required for a natural response to decay by a factor of 1 over E by definition. E is usually given as 2.712, something like that. Okay, so 1 over that will give us 0.37. All right, so all currents and voltage responses, all currents and voltages in terms of the responses of the currents and voltages of the first order circuit decay with time with the same time constant tau. This is very important, so let's pay attention to that. All right. So as you can see here, this is pure mathematics. We know that our V of t is equal to V naught exponential minus t over RC. And then we know our I of t for the RL circuit. This is for the RC circuit, by the way. And then this is for the RL circuit. So you know that our I of t here will be equal to I naught exponential minus R over L multiplied by t. If you start changing the values of your time at t equal to 1, t equal to 2, t equal to 3, t equal to 0, right up till a particular point, you get this kind of a curve. This is the curve you get here, and then this is the curve you get here, all right? So if you do that, that's exactly what happens, and then you can draw this curve up. Again, our tau is equal to RC, and then tau will be equal to L over R here. Tau is equal to RC, tau is equal to L over R here. Okay, so how we obtain this tau equal to RC is what is proved here. Okay, I'm not going to go through this proving. The only thing I think you should know here is the first expression here. This first expression, by definition, this is by definition, okay, 1 over E is equal to V of t plus tau over V of t. By definition, V of t plus tau over V of t is equal to 1 over E. So the rest here is just simple mathematics, okay? You just cross multiply to linearize this expression. Once you do that, this is what you have. And then once you carry out some mathematical manipulations here, or arithmetical manipulations there, you obtain your tau to be equal to RC at the end of the day. So you have tau equal to RC. Also, by definition for the RL circuit, you find out that 1 over E is equal to I of t plus tau divided by I of t. So if you linearize this by cross multiplying, okay, and then you will solve for tau, you will find out that your tau is equal to L over R. Okay, this is also very important to pay attention to. What if we have a situation where we don't have any exponential here, we just have a straight line instead of a curve, we don't have an exponential. This is what you're going to have, okay? So if there is no exponential at all, okay, if you're not dealing with the exponential part of this circuit, you're going to just have a straight line, all right? So that means your V will be equal to V naught minus V naught over tau multiplied by t, and then your I will be equal to I naught minus I naught over tau multiplied by t. If we are not dealing with the exponential part of this circuit, this equation, okay? So let's take it a step further. Now here is an example we can look at. It's an important example. So calculate the time constant tau for this circuit. Use it to find the voltage V for t greater than 0. Okay. in this particular circuit, what do we have? You notice here that we have capacitor here. The capacitor is one of the elements here, and then the rest of the elements we have are resistors, and then we have a DC source somewhere here, right? So this voltage here. What you want to pay attention to is to first of all find the R equivalent here. All right, 2 and 6 are in series, so if you add them together, you have 6 ohms. 6 and 3 are in parallel. If you find the equivalent, it becomes 6 times 3 divided by 6 plus 3, that is 18/9. That gives you 2 ohms here. And then again, the 2 ohms you obtain will be in series with 8 ohms. So that would be 2 plus 8 will give you 10. So the entire, these entire resistors put together will give you 10 ohms. If you find the R equivalent somewhere there, that will give you 10 ohms. Okay, so if you do that, this is what you have. So you have your R equivalent here, and then these for capacitors, you open the circuit, don't forget, okay, just before time is equal to 0. One of the discussions we had in the previous classes is that you can short circuit the inductors, and then you open the circuit for capacitors, if you still remember that conversation. So just before t is equal to 0, you know, our R equivalent, you can have it here, you still have our 15 is here, and then you open this particular circuit. Okay, so if you do that, what you can find is, if you're looking for the V just before t is equal to 0, that will be equal to V of 0 minus. This is V just before t equal to 0. All right, and that will be V of 0 minus. Now, V of 0 minus can be obtained by actually carrying out a voltage division for this particular circuit. To obtain V of 0 minus, you can carry out a voltage division between these two resistances, and then you can obtain your V of 0 minus. Okay, so if you do that, this is going to be voltage V of 0 minus will be equal to, this is V source, voltage source, right, multiplied by R equivalent that we have, because we're looking for the voltage across this place here. So it's going to be R equivalent, which is 10, divided by the sum of all of these R's, which is going to be 10 plus 15. If you do that, you get your V of 0 minus to be 40 volts. And don't forget, in steady state, we always pay attention to continuity principle. So it simply means your V of 0 minus would be the same thing of V of 0 plus, which would also be the same thing of V of 0, by the way, and that would be equal to 40 volts, as you can see. And that will be equal to 40 volts, as you can see here. All right, so now we have been able to handle that. So we know V of 0 plus, we know V of 0 minus, we have R equivalent here to be 10. So the next thing you want to do is to now model a circuit for R greater than 0, for t greater than 0 rather. So now at t, just before t equals 0, we have an idea of what happened. Now what happens when t is greater than 0? What is the aftermath? When t is greater than 0, that would mean that there is no current. This circuit is already opened, and then nothing is passing through this place, right? That's what it simply means. Nothing is passing through this place. So this entire circuit here, there will not be anything going on here. So all we have is just going to be our R equivalent, a simple RC model circuit, R equivalent, and then we have our capacitance, 1 farad here, and the voltage across that. So to find our tau, don't forget we had said our tau will be equal to RC. So in this case, our tau will be equal to R equivalent multiplied by the capacitance. Okay, so our R is 10. We calculated it. Our C is 1, as we know, and tau is time. So eventually our tau will be equal to 10 seconds. All right. Once tau is equal to 10 seconds, we keep that somewhere, and then we go ahead and find the voltage, because we have been asked to find the voltage. And don't forget, our V of t is always equal to V naught, right? It's always equal to V naught exponential minus t over RC. That is our V of t. Since we know that our tau from the previous discussions we had would be equal to RC, by the way, so you can just replace this with tau. Instead of writing RC here, you put tau there, all right? So our V would therefore be equal to V naught exponential minus t over tau. which will be equal to, we found our V naught, by the way, is to be 40, like we mentioned. So we have 40 exponential minus t over 10. Yeah. All right. Or you can write it as 40 exponential minus 0.1 t. You can write it like this if you want, because 1 over 10 is 0.1. So this will be equal to our V at the end of the day. Here we have another example we can examine together, and let's see what this example is all about. We have a simple RL circuit, and we're supposed to find tau. We are supposed to find the time constant tau. We're supposed to find I naught. That is the current when t is equal to 0 is always equal to I naught. So we're supposed to find that. And we know that our current is equal to 2 milliamperes at t equal to 10 milliseconds. And current is also 100 microampere at t equal to 46 milliseconds. And we have been given an RL circuit. Okay, so how do we deal with this situation? We do know that our I of t is equal to I naught exponential minus t R over L. We do know that our tau is going to be equal to this. So we do know that this simplifies to I naught exponential minus t over tau. Now, if you have that, the next thing you want to do is to try to find out what happens at t equal to 10 milliseconds. What happens to this particular equation? We know that our t is 10 milliseconds. So 10 milliseconds is the same thing as 10 over 1000, right? So that's 10 over 1000, and that will be equal to 0.01. So you have, instead of putting t here, it becomes minus 0.01 over tau, all right? And that will be equal to 2 milliamperes here, because we were told that our I is 2 milliamperes. So I of t here is 2 milliamperes. So instead of writing I of t here, you just write 2 milliamperes here, which is 0.002. So we have that as an equation. So if you solve these carefully, what you would have is minus 0.01 over tau, because you're going to take the logarithm of both sides. Okay, and before you do that, you could divide both sides by I naught. If you divide both sides by I naught, you have exponential of minus 0.01 over tau. Okay, this will give us 0.0002 all divided by I naught. If you divide both sides by I naught, so that's what you're going to have. So if you have this, you can then take the logarithm of both sides, or you can take the log of both sides. If you do that, you have ln of exponential of these equal to ln of this entire expression. So ln of this would leave off with just 0.01 over tau, minus 0.01 over tau. All right, if you still remember the mathematics properly, and that would be equal to ln of 0.02 over I naught. Also, if you remember your logarithmic functions and how to solve them properly, when you have division here, you are subtracting two logarithms. Okay, when you have 0.02 over I naught here, it would mean the same thing as when you have ln 0.02 over I naught, it would mean the same thing as ln 0.02 minus ln of I naught. You have that, and then this forms like equation 1, because you're going to do that for t equal to 10 milliseconds, you obtain that. What you will find out is that in this particular equation, there are two unknowns. One of the unknowns is tau, and the second unknown is I naught. Okay, if you look at that properly. All right, let's do that for the second equation, where time equal to 46 milliseconds. All right, so you find out that at that we have I naught exponential minus 0.046, which is going to be 40 milliseconds, by the way, as our time. So you replace t with that, equal to the value of the current at that point, I of t. So you replace I of t with 100 microampere. So 100 over 10 raised to the power 6 will give us 0.0001. Right? So if you solve that, you would also obtain this particular equation here as your equation 2. All right. So if you have two equations and two unknowns, you know exactly what to do. You just try to solve both of the equations simultaneously. If you do that, this is what you're going to obtain. First of all, subtract equation 2 from equation 1. You could use elimination method, you could use substitution method. Okay, for me, if I subtract equation 2, this is equation 2, and the right one at the top here is equation 1. Okay, so if I subtract equation 2 from equation 1, it would mean we start from here. You will see that you have minus lane I naught minus plus lane I naught. Okay, so minus turns this to plus, so that means we eliminate these two eventually. Also, subtracting here will make lane 0.002 minus lane 0.0001. All right, so which is exactly what we have here. All right, and then what else do we have? We have these two left. Okay, so if we have these two left, you are gonna say also that minus 0.01 over tau minus b. All right, so if you do that, that gives you this turns to plus. All right, if this turns to plus, eventually what you will have left is going to be 0.046 minus 0.01, and that will give you 0.036 over tau at the end of the day. All right, so eventually you have minus 0.01 over tau here, you have minus 0.046 over tau here. That's before they carried out this operation here, and you know how we got this already. So if you carry out that operation by bringing these to the other side, it becomes plus. Once it becomes plus and you subtract, you have 0.06 over tau. Once you have that, you know, if you make tau the subject of the expression here, what you would have is 0.036 divided by lane 20, because by the way, this is also going to be the same thing as lane 0.002 divided by 0.0001. All right, just a simple logarithmic, understanding of logarithmic function would take care of it. Okay, so this gives you lane 20, by the way. So if you then make tau the subject, you have 0.036 all divided by lane 20. Again, right from here, everything we are doing right from here downward, everything we are treating is just mathematics. Once you're able to substitute all the values into this equation, the rest is just simple mathematics, simultaneous equation. Okay, so that should not be a big deal for you, and you can solve these two equations with any simultaneous equation that is convenient for you. That's not going to be too important, as long as you do it correctly and you arrive at the right value. So at the end of the day, you will find out that your tau will be equal to 12 milliseconds. So from what you can see here, we found our tau to be 12 milliseconds. And once we found tau to be 12 milliseconds, we can go ahead, because the question says we should also find I naught. Finding I naught would be easy from the simultaneous equation here. I naught is one of the unknown, so we can just go back and substitute. Okay, if you do that, what you will find is this. Using equation 1, you can just substitute the value of tau, 12 milliseconds, into that equation, and then you will find your I naught to be 4.6 milliampere. Now let's talk about general first order circuits without sources. General first order circuits that do not have sources. All right. Now we can apply the previous techniques to circuits that can be reduced to simple RL or RC circuit. So here is a simple example to deal with that. Find the time constant of the circuit below. You will find out that we have two resistances, and then you have two capacitance here, and then we have one resistance to the right. So that makes it 3 resistances in the circuit and two capacitance in the circuit. And we want to find the time constant for this particular circuit. First of all, you can convert this particular circuit to its equivalent. If you want to do that, you find out that these guys here are in series. 4 plus 1 is 5, and 5 and 20 ohms will be in parallel. So if you deal with them that way, total resistance in the circuit, or R equivalent, will be 5 parallel 20, and that will be 5 times 20 over 5 plus 20. That gives us 4 ohms. Okay, so your R equivalent is going to be 4 ohms here. Also, for the two capacitance, we do have, they are in series. So to find their equivalent, you treat them like you would treat resistances in parallel. So it becomes 4 multiplied by 12 divided by 4 plus 12. That gives us 3 farad. Okay, so your C equivalent is 3 farad, and then your R equivalent is 4 ohms. So that would mean that your time constant, tau, like we said earlier, is going to be equal to R equivalent multiplied by C equivalent, or R multiplied by C. So you have 3 multiplied by 4, and that gives us 12 seconds. This is pretty much a straightforward example. All right. Now let's deal with another example. The next example, find the time constant of the following circuit. So what you see here in this circuit is that we have an inductor of 38 millihenry, and then we have another circuit to the right here with about 5 different resistors. Each of them has one resistance, and only one has two ohms. 1 ohms resistance each for the ones at the borders, and then the one right in the middle here is 2 ohms. Okay, so what you want to look at here is you never can tell if these guys are in series or if they're in parallel because of the nature of this particular circuit. So the way we will deal with them, the way we will find the R equivalent here will be a little bit different. Normally we need the R equivalent here to be able to find the time constant. We need the R equivalent because normally for an inductor or in an inductive circuit, your tau normally is supposed to be equal to L over R. This is what we're supposed to have. Okay, so to do this, we know our L. We need to find the R equivalent here, but we don't know if these guys are in series or parallel. So let's see. Let's go ahead. What you find out is that first find the equivalent resistance connected to the terminals of the inductor. I've explained that. Since the resistors are neither in parallel nor in series because of their configuration, we cannot directly calculate R equivalent from here. Instead, what we can do is to find the ratio between a test voltage and a test current. Okay, so finding the ratio between a test voltage and a test current would mean that we want to find V over I. As you know that our V is always equal to IR. We know that already. So if you want to find your R, in any case, it will be equal to V over I. So what we want to do here right now is to find V over I in this particular circuit here. And once we're able to do that, whatever it gives us automatically becomes our R. That's what we want to do. That's what we mean by finding the ratio between a test voltage and a test current. All right. So let's take it a step further from here. How do you do that? You create a loop, okay? So this becomes loop 1, this becomes loop 2, all right? And then what you do to do that, you create a test voltage here and a test current, okay? So that means you put the source here, all right? So when you do that, you can see that we have our voltage here, which is going to be the test voltage. You have our current here, which is going to be a test current, okay? So and you can let the current move in this direction, and then you have a loop here, you have a loop here, so you can actually put a current here passing through this loop, make it I1, the current passing through this loop, make it I2. Okay, so you have V here, you have I here, and these are our test responses that we do have, the test responses that we have, voltage and current. So for mesh 1, the current that is passing through this resistance, the current passing through this resistance will be, since we are dealing with mesh 1, it will be I1 minus I, because this is actually I. So it will just be I1 minus I multiplied by 1. That is why we have this here. And then for this 1 ohms, you see that only I is passing through this 1 ohm. So you have I1 multiplied by 1. You have this here. And then for 2 ohms, you see that you have I2 is passing through 2 ohms, I1 is also passing through it in opposite direction. So since we're dealing with this first loop, it becomes I1 minus I2. That's the difference between the two currents. I1 minus I2 multiplied by 2 gives us the voltage across these two ohms. All right. So this is the voltage across this 1 ohm here is I1 minus I1 multiplied by 1. That's it here. Voltage across this 1 ohm here will be I1 times I1. This is voltage. This times 1, so this is voltage here. This is I1 minus I2 times 2. This is the voltage across these 2 ohms. You equate it to 0. And then if you solve that and rearrange it, you have 2I1 minus I2 equal to I over I2. You do the same thing for mesh 2. For mesh 2, you find out that The current I is also passing through this 1 ohm, and then this I2 is passing through this 1 ohm. And since we deal with this mesh, we have I2 minus I1 multiplied by 1. This is the voltage across this 1 ohm. Also, voltage across this 2 ohm will be I2 minus I1 multiplied by 2. That's the voltage across this 2 ohm as far as the second loop is concerned. And then for voltage across 1 ohm, it will just be I2 multiplied by I2 multiplied by this 1 here. Okay, that's going to be the voltage across this 1 ohm. Okay, so that would be I2 times 1, and then this is supposed to be 2. This is supposed to be just I2, not 2I2. All right, this is just supposed to be I2. If this is 2, if this is 1 here, this is just supposed to be 1 times I2. So this is not supposed to be 2I2. Please pay attention to that. So there must be something wrong here. Let's just assume that means they are assuming this is 2 ohms. That's what it simply means. In your note, to make this more straightforward for you, in your notes, you can just make this, change this 1 ohm to 2 ohms in your note. Change this 1 ohm here to 2 ohms in your note so that it will be easy for you to follow. So if this is 2 ohms, that simply means the current passing through here will be 2I2, and that's exactly what we have here. You equate everything to 0. So you get another equation here, 5I2 minus 2I1 equal to I. All right. So if you add these two equations together to eliminate I1, because I1 here is 2I1, I1 has a coefficient of -2, it has a coefficient of +2 in the first equation and coefficient of -2 in the second equation. So it means if you add them together, you're going to cancel and eliminate everything that has I1. So that simply means you're left with, if you add together 5I2 minus I2 gives us 4I2, and then what you have here is I over 2 plus I, that gives us 3 over 2. So we have 4I2 equal to 3 over 2I. And eventually you can make I2 your subject. I2 becomes 3 over 8I. This is just pure mathematics, it's a simple simultaneous equation. So if you substitute for I2 in equation 1, you can find your I1 to be 7 over 16I. So we found I2, we found I1, all right? We found I2, we found I1. So the next thing you want to do is to apply KVL to the entire loop. If you apply KVL, you find out that you have minus V, right? Because we're moving clockwise this way, you have minus V, all right? The current, the voltage across this 1 ohm right now, since we are now dealing with this particular loop here, so this current takes precedence. So you have plus 1 times I minus I1. Now that's going to be current passing through. That's going to be current passing through 1 ohm, I minus I1, that multiplied by this 1 ohm will give us the voltage across this 1 ohm. Then the voltage across this other 1 ohm will be I minus I2 multiplied by 1 again. So you have plus 1 times I minus I2 again. Okay, that would give you the voltage across here. And then eventually you would have to equate everything to 0. You would have to equate everything to 0. Okay, so you equate everything to 0. That's going to be KVL. That's the KVL in this particular loop. Minus V plus V's and then plus D's equal to 0. If you rearrange, it simply means your V will be equal to, if you take V to the other side, will just be equal to I minus I1 plus I minus I2. That is what your V will be. So your V will just be 2I minus I1 minus I2 would be our voltage, all right? So keeping that in mind, you find out that we already know our I1 to be 7 over 16I. We know our I2 to be 3 over 8I. We all have them in forms of I, and we have 2I here. If you bring those into this equation and then you just add and subtract, you would obtain 19 over 16I. So eventually your V will be equal to 19 divided by 16I. All right, dividing both sides by I would mean you have V over I. This will be divided by I. This I will cancel I. So your V over I will be equal to 19 over 16, and this will be the same thing as your R, which is the R equivalent that we are looking for this particular circuit. Yeah. So our R equivalent will be equal to V over I, which is the same thing as 19 over 16. Now that we already have our R equivalent, it makes life easy for us. What we are actually looking for is the time constant. Don't forget, what we are looking for is the time constant. So we had to travel this way, and we know our time constant will be equal to L over R. So we had to travel, this journey to find our R, and we already know our L. If you remember, they gave us our L in the question. So our time constant tau will be equal to L over R, which will be equal to 0.038 as given in the question, divided by 19 over 16, and that gives us 0.032 seconds. That is the same thing as 32 milliseconds, by the way. So this is how to find a time constant for this kind of a circuit. All right. So here is an example that we should deal with together. We have been given a circuit on the left-hand side, as you can see, and then we have been asked to find the equivalent resistance of the circuit. All right, at the terminals A and B, the equivalent of resistance below the terminals A and B, as you can see here. Then find V of t for t greater than -1. If V of -1 is 20 volts. So when the time is -1, the voltage is 20 volts. So find V of t for t greater than -1. All right. So this is what we're going to quickly deal with as we move on. All right. So the first thing you want to do is to apply KVL to the loops. Okay, we have two loops here. If you apply KVL to the loops, what are we going to have? First of all, you could apply KVL here, and then you're gonna have this is a loop here like this. You could apply another KVL here, and then you have a loop like this. Okay, so for the upper loop here, you can see we have I equivalent here at the top here. So what you would find out is that our loop current is actually in opposite direction to I equivalent here. All right, so. And these 3 ohms, the I equivalent here will be the same thing as point B here, except that it's going to be minus here. So this is going to be like a positive terminal. This is going to be like a negative terminal, all right? What you will find out is that here we have, if we are starting from here, what we are going to have is, so if we are starting from -5, what we are going to have from 5 ohms, because this is positive terminal and this is negative terminal. This is positive because you can see the current coming down through this way. Okay, so what you can have here is you have -5 equivalent, right? And then you have, since the current also, this loop current is also in opposite direction to the I on this 1 ohms, this becomes -I, and then that would become -1 times I, right? And then if we continue, you will find out that we get to IQ here, 3 ohms also. This loop current is opposite IQ, so you still have -3 times I equivalent. All right, so what you're gonna have is -3 I equivalent. Okay, here it's going to be -5 I equivalent, by the way. Okay, so this is what you're going to have here, and then you're going to have plus B equivalent here. Everything has to be equal to 0, right? So do you all understand exactly what is going on here? This is what the equation would look like. Everything would be equal to 0, all right? So if you rewrite these and you want to make VQ the subject of the formula, what you are going to have is V equivalent will be equal to -5 minus 3 will give us -8. If you take -8 to the other side, this will give us 8 I equivalent, okay, and then plus I times 1 will certainly just be I. All right, this is what you're going to have. So this is labeled as equation 1, as you can see here. This is labeled as equation 1. That's exactly how we got this equation 1 here. All right. So if we take it further, You keep that equation somewhere, and then you try to check out the other loop we have here. We have a second loop here. This is loop one. Okay, this is like a loop two. We have a second loop here, or you can call this loop A, and this is loop B, whatever it is you want to call it. Okay. What you would find out for this other loop here, you see that we do have current I already passing through 1 ohms, and then we have 2I here. All right. This is a voltage source, and then we have 1 ohms here. We have 1 ohm here. All right. So if we start from here, you can say that starting from the 2I source, you have minus 2I, right? And then if we go down, you realize that, okay, now before we go ahead, let me try to, we have to solve, there's a problem here we have to solve. There's a current coming in, this is a node, don't forget, we can treat this as a node. So we don't have any current defined in the second loop. Okay, so we have to define it ourselves. So this is a node. So we can apply KCL at this node. We know the current coming into this node. We know the current leaving this particular node. Okay, so we can say let there be another current going down in this particular node here. Okay, so if we have it like this, this is what we are going to have. If we have it like this, then we can say that for KCL, if you apply KCL to that loop, what you're going to obtain is current leaving. For example, if you choose to label this particular node, if you want, you could label it I2. If you want, you could label it I2. So let's say I2 is coming. No, don't label it I2. Let's label it. Let me try to put it here. Let's label it. Let's just call it IA. Okay, the current passing through coming down from here. Let's label it IA. So if you have that, for our KCL, we can easily say we have current coming into that node will be negative. So you have minus I equivalent, right? So I is leaving, so that is going to be plus I, right? Because I is leaving that particular node, plus I, and then what else again do we have? Now IA is also leaving the node, so that is going to be plus IA, isn't it? Plus IA. Okay, so you have plus IA. In this particular case, everything has to be equal to 0. So it's equal to 0. So we are looking for IA. We can easily say that our IA would be equal to IEQ minus I. So this becomes our IA. We can easily say this. Okay, so once we have this, we can then go ahead and apply our KVL, right? So if we say now for the KVL in the second loop, what we're gonna have is you can say we have minus 2I, all right, then plus, now the current passing through this 1 ohm here will put the same current passing through the second 1 ohm right at the bottom here. Okay, so and that current is actually against the loop current that we created, that we know polarity that we created. So you could say that we have minus 2I minus, so this time around it's going to be minus instead of plus because it's against that current, minus that resistance 1 multiplied by that current passing through the 1 ohms. We found it to be IA, so you can call it, and we know our IA is IQ minus I, so you can call it IEQ minus I. Then you can close your bracket, and then you go ahead to the second 1 ohms. You have another one that's minus 1. The same thing would happen there. You have IEQ minus I, exactly, yeah. So everything has to be equal to 0. Before we equate it to 0, there's another I right at the top here. There's another 1 ohm in that same loop at the top here, right? So that gives us minus I. So that gives us, since the loop current is going to be in the same direction with that particular current, so that is certainly going to be a plus. So that was going to be plus I plus 1 dot I equal to 0. Exactly. This is exactly what we are going to have here. All right. Are you guys following? So if we have it like this, then the next thing you want to do is to quickly solve that and then rearrange. So what you would have is minus 2I minus 2I minus 2 IEQ. If you expand the bracket, Okay, let me do this way to make it easy. Minus 2i eq minus 1. This will make it easy for everybody. Minus 2i eq minus I, not 1, plus I. All right, this is going to make it easy for all of us. Then this is going to be equal to 0. Okay, so with this in mind, you can then go ahead and say, okay, you have minus 2i. If you expand that, minus 2i equivalent, right? Then another minus 2, this becomes plus now, because if you expand that, it becomes plus 2i, then plus I, right? That would be equal to 0. Okay, so what is going on here? If you rearrange, you will find out that this minus 2i will cancel this minus 2i. So what you're going to be left is going to be minus 2i equivalent plus I. So you can easily say that your I would be equal to 2, let's see, 2i equivalent. Okay, so that if you rearrange, this is exactly what you're going to obtain, because eventually what you will find out is that this minus 2i will cancel this 2i here. So you're left with just I, and if you take minus 2i equivalent to the other side, you're left with minus I equal to 2i equivalent, which is exactly what we obtained here as equation 2. So I've been able to show you how we got equation 1 and equation 2 from here. So if you combine equation 1 and 2 by substituting I equal to 2 equivalent into equation 1, what you would eventually find out is that V equivalent would be equal to 8I equivalent plus I, and I is 2 equivalent. So that would mean V equivalent would be equal to 10. V equivalent will be equal to 10I equivalent. That's what simply means. This here will give us 10I equivalent. All right. So then you can easily say that your V over I will be equal to 10. Your V equivalent over I equivalent will be equal to R equivalent that we're looking for, which we have been asked to look for in the A part, and that would be equal to 10 ohms. Okay, so this is how to find the R equivalent for this kind of a circuit where we are not entirely sure what is going on. It is hard to know which one is in parallel with which one and which one is in series with each one. And then even if we do know the configuration of this particular circuit, make it difficult for us to be able to find R equivalent directly. So this is how we can carry out, cases like this, and then we can find our R equivalent. We have been asked to find V of t for t greater than minus 1 if V of minus 1 is 20 volts. So how do we deal with cases like this? We know that our V of t is equal to V naught exponential minus t over RC. We know this already. So now this would be the same thing as V naught exponential minus t over, now our R, what is our R? Our R is 10 ohms. Okay, so this is the 10 ohms here for our R, and then our C is going to be 10 millifarad, which is 10 over 10, right? 10 over 1000 rather. 10 over 1000, that will give us 1 over 100, and that is simply as 10 raised to power minus 2. So that's exactly where this 10 raised to power minus 2 came from. If you multiply that, what you're going to be left with is V naught exponential minus 10t is what you're going to be left with at the end of the day. Now, we were told that V of minus 1 is 20 in the question. So that simply means when t is minus 1, our voltage is 20 volts. Substitute t to be equal to minus 1 would mean we have minus 10 times minus 1 here. So we have exponential 10. So what you would find out is V of minus 1 is equal to 20, which is equal to V naught exponential 10. So if you equate these two together, what you're going to come up with is the value of V naught. You can find your V naught from this expression. V naught will therefore be equal to 20 divided by exponential 10. By the way, if you have a calculator, you can try to find out what this would look like. You can get a specific value for this if you have a calculator, or you can leave it like this if you find yourself in an exam. So this is going to be 20 over exponential 10. So once we know our V naught, we can come back to this particular expression and say, okay, V of t would therefore be equal to 20 divided by exponential 10, which is our V naught, exponential minus 10t, because we do know what R is, we know what C is, and then we put those, this is what we get. If you want to rewrite this entire expression, you can rewrite it. It becomes 20 exponential minus 10 t plus 1, because we have the same power here, 10, 10. So it becomes easier for us to rewrite it in a linear form, and this becomes our V of t when t is minus 1. Okay, so let's take it a step further. So now we want to talk about DC. We want to talk about circuits with DC sources. All right. So when we have circuits and those circuits have DC sources, how do we treat those? Circuits driven by constant DC independent current or voltage sources in addition to having initial stored energies are going to be evaluated now, and we'll go through it together so you can have a perfect understanding of how to deal with stuff like that. Now, if V of 0 minus is equal to V naught, V of 0 minus would mean that, okay, this is what is happening in the circuit before the circuit is either closed or opened. Okay, so if the circuit was open before, okay, so V of 0 minus would tell us exactly what is happening before the circuit is closed. The circuit is usually closed when T equals 0. All right, so for this particular circuit, it means the circuit was, opened before T equal to 0. At T equal to 0, the circuit is closed. That's what it simply means. So if V of 0 minus is equal to V of 0, then V of 0 plus is also equal to 0, following the continuity principle that we talked about when we started this teaching. So for T greater than 0, KCL at the top node, this is the node we're talking about here, KCL at this node would mean that current coming in would be negative. So you have minus I naught, that is what is coming in here. And then you have a current leaving here, and then you have another current leaving here. All right. So what you will find here is that we have current passing through R will be equal to V over R according to Ohm's law. So we have V over R here. Current passing through the capacitor we have here, this capacitance here would be equal to C divided T. So that would mean that we are adding these two currents together and then minus this, because these two other currents, or these two currents, are actually leaving the circuit. So they have plus signs. This is coming coming to the node, and then it's going to be having negative signs. The other two currents are leaving the node, so they're going to have plus signs. So if you rearrange these, what you would come up with is dv T plus 1 over RC. This could also be V over RC, by the way. This also means V over RC equal to I naught over C. So this is like a differential equation, first order differential equation, like we discussed the last time. So this is not a problem for you guys at all. If we take it further from here, what you will find out is that forcing time independent of the unknown time functions is what this I naught over C, that is what it represents. It represents the forcing term, which is independent of the unknown functions. Okay, so let's take it a step further from there. So we need a trivial V where a linear combination of V and its derivative is constant for all T greater than 0. So we can find a first solution V of T, and then would say, we can make an assumption and then say, okay, let that first solution be equal to A. Okay, let it be equal to A because it's going to be a constant. So we say, let the first solution be equal to A. The full solution is supposed to be V of T, by the way. So, and this V of T would have both forced solution and unforced solution. The unforced solution is going to be the natural response of the circuit. The forced solution would be the response of the circuit because of the voltages, the independent voltages that we have in the circuit. But then without the independent voltages, what we're going to have is going to be the natural response. Okay, so the final response V of T of circuit would be this first response plus the natural response. So first of all, we want to try to find the first solution now. So let's say the first solution is equal to A, an assumption that we have made. So wherever it is we find our V, we're going to put A there, especially in this particular equation. So if you put A here, instead of writing the V, we have the A, the T plus 1 over RC multiplied by A, which is the same thing as A over RC, as you can see here. Once you put those here, equal to I naught over C. A is a constant, like I mentioned earlier. So if you differentiate a constant, ddt of A is going to be 0. So that is why this is going to disappear once you differentiate these. So you're going to be left with A over RC equal to I naught over C. If you make A the subject of the formula, because we're looking for A, or the subject of the expression, this C will cancel this C. And what you're going to have left is A equal to I naught multiplied by R. I naught R is going to be our A. Okay, so that simply means our V of T can be said to be equal to I naught R. This is the first solution based on the independent DC voltage or current that we have in the circuit. So now that we have the forced solution, we can then go ahead and find the natural response or the transient response or the unforced response. Those are different names you probably might want to call it. All right. So if you want to do that, that simply means at that particular point, you can equate the V t plus 1 over RC V. You can equate it to 0. This time around, you can replace your natural response, which is V. You can say your natural response is equal to Vn. So you can replace that with Vn. So whenever you see V, you just put Vn there to denote that you're talking about a natural response. All right. And a natural response automatically, helps us to get our characteristic equation. So in that particular case, this is going to be equal to 0 for a natural response. This entire equation here will be equal to 0. Okay. So a valid differential equation must satisfy V of 0 minus equal to V of 0 plus equal to V naught. Okay, V naught would mean that when our t is equal to 0, we obtain a V naught. Okay, so that's what we have here. So let Vn of t denote any solution to the unforced differential equation. So wherever you see V, you put Vn there. So you have this equation, the Vn, the t plus Vn over Rc. This time around, it is going to be equal to 0 because we're talking about a natural response. So the entire stuff here is going to be equal to 0. All right. So our Vn, as we have calculated previously, is equal to K exponential minus T over Rc. We can try to prove it again. All you need to do is just you rearrange this. The Vn, the T plus Vn over Rc becomes minus Vn over Rc. You take the exponential of both sides, integrate both sides, and then do whatever it is you need to do. You will find Vn to be equal to K exponential minus T over Rc. We proved this earlier too. So if you have this, that means you already have two equations already. Okay, so you have Vn and then you have Vf. Vf represents the first solution, Vn represents the natural solution. Your total V will therefore be equal to your Vf plus your Vn. That is what your total voltage, your total response would be. So if you do that, this is what it would look like. So your total V would be equal to Vn plus Vf, which is equal to K exponential minus T over Rc plus Ri naught if you combine those. And since we know that our V0 plus will be equal to V naught, and from the question we were given some parameters, okay, from when we started, we were given some parameters, which are these. If V naught minus equal to V naught, then V naught plus equal to V naught. Okay, we came up with this when we were talking. Okay, so you will find out that you can find the value of your K. All right. So when V naught equal to V naught plus V naught plus, when V naught plus equal to V naught, it simply means at this time our T equal to 0. That's what it simply means. So when T is equal to 0, whatever it is you find T, you put 0 there. If you put 0 here, everything here becomes 0. Exponential 0 becomes 1. That's why we have K multiplied by 1 here, then plus Ri naught. All right. If you rearrange these, you will find out that your K would be equal to V naught minus Ri naught. If you pick these and bring it back to this particular equation at the top here to replace with K, you find out that your V of T will be equal to V naught minus Ri naught exponential minus T over Rc plus Ri naught. Okay. In this particular equation, what you would notice here is that if you make T equal to 0, all right, you will find out that your V of T will be equal to V naught at the end of the day. Don't forget, if T is equal to 0, this becomes V of 0, right? This becomes V of 0, and this would certainly be equal to V naught, all right? So if you make T equal to 0, put T here. Everything here becomes 1, all right? So you have V naught minus Ri naught plus Ri naught. Eventually, all of these here will cancel out, and your V of T will still be equal to V naught. You still have it to be equal to V naught here when T is equal to 0. All right. So here is the summary of how you can deal with the problem. I've explained that to you, so we don't need to talk about this anymore. You can just read this and get an understanding. So let's quickly solve one or two examples. So we have a question here where it's trying to find I of T for T greater than 0. When T is equal to 0, that is when this circuit is opened, as you can see here. When T is equal to 0, that is when this circuit is open. So t equal to 0 minus would tell us what is happening before the circuit was opened. So assume that before t equal to 0, the circuit has been in steady state before the circuit was opened. Okay, that simply means that what we're going to have here is going to be a short circuit. If it were to be a capacitor, it would be an open circuit here. Okay, so yeah, so at t equal to 0 minus, we can easily find the current IL for this inductor. We can find that how. That current, we can find it. For example, if you take this place to be a node, all you need to do is just to apply KCL. If you apply KCL here, what you would find out is that you have the current passing through these 2 ohms resistance will be equal to 12 divided by 2, as you can see here. The current passing through these 4 ohms resistance will be 16 divided by 4, as you can see here. So that will be the current going this way, all right? And this will be the current coming this way. And then this will be the current going this way, or IL. So IL will be the only current leaving the circuit, all right? The other currents are coming into the circuit. If you apply KCL, it simply means that you have 12 over 2, you have minus 12 over 2, all right, minus 16 over 4 because they are coming into the circuit. And then IL is leaving plus IL, everything will be equal to 0. So if you make your IL the subject of this entire equation or expression, this is what you are going to have at the end of the day. And that simply means your IL would be equal to 10 amperes. That would tell us, for if you pay attention to continuity principle, if you apply the continuity principle, you find out that your IL will be the same thing as IL plus, which will be equal to IL minus, which will be equal to 10 ohms. So you have these, you can keep it somewhere. Now, this is what happened in the steady state situation just before the switch was opened. This is what is going on in the circuit. Okay, now let's go ahead. So now that the circuit is open, it simply means t is no longer equal to 0. T is now greater than 0. In this particular case, what you want to do is to find the first equation. This time around, we will pay attention to what is going on in this left-hand circuit, because once this circuit is opened, it simply means there is nothing happening in this particular circuit. This circuit is redundant, all right? Okay, it is open. So if it's open, nothing can pass through this particular switch. When this switch is opened, rather, nothing can pass through this particular switch. So what you have left is just going to be the circuit to the left. You have your DC12, you have your 2 ohms and 1 Henry inductor. So applying KVL would mean that you have minus 12. Okay, if you have your loop like this, it means you have minus 12, right, plus 2 multiplied by I. This is going to be the voltage across the 2 ohms resistor. 2 multiplied by I. And then for the inductor, you do know that our V is always equal to L di. Our V for the inductor, V is always equal to L di dt. So in this particular case, our L is just 1 Henry. So if you put 1 here, everything is as good as not having anything here. That is why we have just the IDT here. And then for the loop, addition of all those voltages must be equal to 0. If you rearrange all of these and you write it in the form of first order differential equation, starting with the IDT, this is what you are going to obtain. So you have this first differential equation. Again, what you want to do is to find the first response first of all. After finding the first response, the second thing you're going to do is to find the natural response, and then afterwards you add both the first response and the natural response together to get the entire response of the circuit. So what we want to do right now is to find the first response. In this particular case, the first response, IF, you can select IF be equal to A. That's going to be the first response, the first solution to this particular circuit. So if IF is equal to A, you have the IDT here. IF is equal to A. That means whenever you find I, you put A there. If you put A here, you're going to have the A, the T. A is the constant. Everything here becomes 0. If you differentiate the constant, you get 0. That is how this 0 came about. Here also you put A here instead of I. So you have 2A equal to 12. That's what is left. And then you can say your A would be equal to 6. So if A is equal to 6, that is going to be the first solution that you have. Now, on first equation, what you find here is that we had said from previous discussions that the natural solution is just going to be equal to KEST. I remember I explained this to you guys specifically, telling you why it is important that we're going to use it a lot, because it is a solution for our characteristic equations. Okay, so what you do is, in this case, for natural response, wherever you see I, you put IN, where N represents natural. So you have the IN, the T plus 2IN. It will be equal to 0. For natural response, this is not going to be applicable. It will be equal to 0 because this DC, natural response, we are assuming the DC is not available. It's not in the circuit for natural response, because that is exactly where we started from. Okay, so this would be equal to 0. So the characteristic equation for this is S plus 2 equal to 0. I don't think you need me to prove this to you anymore, because by the time you work on this, what you are going to obtain is SK. You're going to obtain SK exponential ST. I've done this before. So SK exponential ST plus 2, right? Exponential ST. That is what you're going to obtain, okay? Equal to 0, okay? I think it's going to be plus 2K exponential plus 2K. So eventually what you would have is K exponential ST, all right? Then you open the bracket, you have S left here, you have plus 2 here. Everything would be equal to 0. So in our quadratic, from a mathematical understanding of quadratic expressions, it is either this is equal to 0 or this is equal to 0. And these can never be equal to 0. By definition, K exponential ST cannot be equal to 0. So the only thing that can be equal to 0 is S plus 2. That is why we usually just forget about this, and then we go for S plus 2 equal to 0. And then you get your natural, you get the value of your S to be equal to minus 2. Once you have that, it simply means the natural solution will just be K exponential minus 2t. This becomes the natural solution, K exponential minus 2t, because we found the value of our S to be equal to minus 2. Okay, so once you have that, the next thing you want to do is to go ahead and say, okay, you have a natural solution, you have your first solution. What next? I of t would be equal to the natural solution plus the first solution, and that would give us Ke exponential minus 2t plus 6. All right, that becomes the final solution to this. Now, if you go back to what we started with, you will find out that we said that our IL equal to 10. That means our IL 0 plus equal to IL 0 minus, which would also be equal to IL 0. This would also be equal to IL of 0. Okay, so that simply means that when t equal to 0, this is what we are going to obtain. If you do that, that simply means that if you say t, let t be equal to 0, okay, so that means this is I of 0. All right, and that would be equal to 10. That's what we calculated here. Okay, so that would mean that I of 0 plus would be equal to 10. All right, and that would mean you equate everything here to 10. That is what it simply means. You equate everything here to 10. All right, but we're looking for I of 0. That simply means t is 0. So you put t equal to 0 here. If t equal to 0, that means everything at the top here would be 0. Exponential 0 would be 1. K times 1 is k. So you are left with k plus 6 equal to 10. So your k will definitely be equal to 4, mathematically speaking. So once your k is 4, it simply means that you can come back to this equation here and say that instead of writing k here, you just replace that and put 4 there. K equal to 4, this represents your I naught. All right, kind of. Okay, so that simply means I of t would be equal to 4 exponential minus 2t plus 6a, and this would mean the total response in the circuit. All right,